Welcome to the Distinguished Scholars Academy.
From wherever you're watching from, welcome to the Distinguished Scholars Academy YouTube channel. So today we have chemistry, and our topic for today is going to be under chemical equilibrium. We are going to be looking at a very important concept in chemical equilibrium, and you may guess right or not, but that is the solubility product, KSP. Alright, welcome back. We are looking at solubility product under chemical equilibrium. Solubility product. That's the KSP. Alright, let me quickly take you back through a bit of chemical equilibrium. When we talk about chemical equilibrium, we know it's a type of dynamic equilibrium where a system is said to be in a state of balance. And in this case, we talk of three major conditions for a system to be in equilibrium. It must be reversible, it must be in a closed system, and the rate of forward reaction must be equal to the rate of backward reaction. All of that aside, you also know that there is the popular Lo-Chatelia's principle that whenever an external force is introduced into a system in equilibrium, what happens? The system will readjust or annul itself to neutralize the effect of the external force. That is, you are swinging on a JAMB rover, and then someone suddenly comes and jump on the other side. What happens? You need something to balance it up so that the whole swing does not fall over. But that's that. There are three things that can affect the position of equilibrium: the temperature, the concentration, and the pressure. But we are not all about that today. Maybe in the next video, please keep an eye on that. Now for today, we are going to the solubility product. How do we come about the solubility product? First off, you must know that when you are thinking of equilibrium, there is something called the equilibrium constant. If you remember very well, if you've read this topic, you would have come across the statement that the expression of equilibrium constant is based on the law of mass action. Yeah, you're right. Alright, law of mass action, and then from there we came about the fact that mathematically the equilibrium constant is the concentration or activity of product over that of the reactant. What do I mean by that? For instance, you are given this reaction A, let's say it's a solid, plus B, which is a gas, reversible Y in equilibrium, to give us C, which is aqueous. Now, from the law of mass action, the equilibrium constant KEQ will be equal to concentration or activity of product over concentration or activity of reactant. So what do we have on the product side? That's C. Okay, what do we have on the reactant side? We have A and B, but I'm going to be choosing just B. Why am I doing that? You can quickly type that in the comment section and tell me why am I not putting A in that. Alright, pause the video, whatever is your answer, let's see if you are correct. So for the A part, why am I not putting it? Remember, or you could simply read that up, we do not add pure solid or liquid when writing expression for equilibrium constant. And of course, if we have number of mole, it's another different case entirely. Now, for instance, let's say I have 2A plus 3B to give me 4C. This is an instance, a hypothetical reaction. In this case, what will happen is that the number of mole will be a power of my concentration. That's why I said concentration or activity. When you have the concentration raised to power the number of mole, it is called the activity of that species. So this is going to be activity of the product. So it's going to be C raised to power 4. And then when you get here, it's going to be what? B raised to power, exactly, that's B raised to power 3. Alright, now that's basically like the concept of equilibrium constant. If you do not know equilibrium constant, you will not be able to understand why we are here. That's why I'm taking my time to explain this concept. So let me give you one example, you try it, and then let's see if you understand that already or not. Alright, so the example is in the reaction of the Haber process. Write the expression for equilibrium constant. So what's the Haber process? That's the industrial production of ammonia, and the equation is given by N2, which is definitely a gas, with 3H2 gas, reversibly giving us 2 moles of ammonia gas likewise. Now this is not going to be difficult because of course everything is homogeneous in the gaseous state. Remember the catalyst that's finely divided ion catalyst, but of course that makes it heterogeneous equilibrium. You can read that up. Now yeah, what do you think is going to be the equilibrium constant of this reaction? Quickly do that. You can pause the video and send your answer into the comment section. Now let's take it quickly together. Okay, we have KEQ, equilibrium constant, equal to, as usual, activity of product over activity of reactant. I'm not calling the concentration because of course it will be raised by the power. That's based on the law of mass action. So you have KEQ equal to what's the product? That's ammonia NH3 raised to power of 2 all over what we have on the reactant side. This time around we are putting this because of course they are both gases. So we have 1 mole of N2 and hydrogen gas H2 raised to power how many moles? 3. Alright, so I want to believe that you are very, very clear on this concept when it comes to writing equilibrium constant of reactions. Now let's move on to today's business of the day. So the solubility product, what do you mean by solubility product? Of course, the solubility product is a kind of concept that is used to describe solubility of sparingly soluble salts. Okay, and there's this popular question that says that why does KNO3 not have solubility product? Essentially, the reason why we have no solubility product for KNO3 is because it is very, very soluble. You get potassium nitrate. Essentially, all nitrate salts are very, very soluble. Okay, read that up in your quantitative and qualitative analysis. Now let's come back to this. So solubility product applies to sparingly soluble salts. Sparingly soluble salts. So you need to know a couple of them before you can do that. But how does it work? Now let's say we have a sparingly soluble salt, ANBN. Now because it is sparingly soluble, it's going to be in the solid state. Of course, sparingly means that it is almost not soluble. You know, when you're studying solubility in your new school chemistry that we popularly call Ababio, you come across readily soluble, you come across fairly soluble, and you come across sparingly soluble. It tells you that sparingly soluble is like the least soluble state of any stuff. So this salt is sparingly soluble, meaning that even if it will dissolve, it's just like out of 100 pellets, only 1 or 2 is dissolving. So yeah, so this is sparingly soluble salt, and because it is under equilibrium, even if it is just 2 pellets that dissolve, that 2 will ionize. So when this ionize, you're going to get okay, that's going to be, now I don't want to write the answer. This is what I want you to learn. When you have ANBM, you know, sometimes some of you may not even know how to ionize this salt. So how do you learn the ionization? Now whenever you have something like this, write out the subscript. The subscript for AN is N, subscript the number below, sub, okay, and then BN, the subscript is M. Now whenever elements combine, they do so in simple number ratios to one another, and of course they exchange their valencies. So it means that this N that is under A is actually not the valency of A, it was gotten from B, and this M was gotten from A. So by the time you ionize it, the first one is positive, the second one is negative. So this means that A initially is what? AM plus, and B is what? BN minus. Now let's bring it down to practical stuff. Think of something like CaCl2. Now when you look at CaCl2, the subscript here is 1 for calcium, and then for Cl it is what? 2. So basically this is here, this is here. So this is going to be Ca2 plus and Cl minus. Now while you are also trying to do this, you must, if you can balance the charges, then you must also balance the atoms. So this is going to be 1 Ca, how many chlorine? 2. So 2 Cl minus. Now let's come back to our business. So you have ANBM now. Let's say we are using the same method, ANBM. The subscript is N and M for A and B. So this is going to be AM plus Bn minus. Now, but how many moles of A do you have? N. You have N moles. How many moles of B do you have? You have M. So when I ionize this, I'm going to get NaM plus and M, okay, Bn minus. I believe that's clear. Don't worry, we're going to apply chemical equations and we are going to get this properly. So now, anytime you have ions, that is charged substances, they are always going to be aqueous. You can check out what do you mean by aqueous. I mean, what does it mean when you say something is aqueous? Well, to save you that stress, aqueous is simply a solution where a solute is dissolved in water. As long as water is solvent, it's called an aqueous solution. Now you come back to this, how do you write the equilibrium constant? Of course, we already did that earlier. That's activity of product over activity of reactant. And so we take that, that's going to be A raised to power M plus the number of mole is definitely the product, that's why it is called activity. So that's going to be raised to power N, and B N minus raised to power M. It's supposed to be over this, but this is a solid because it's a sparingly soluble salt, so we don't consider this. So anytime you're writing equilibrium constant for sparingly soluble salt, which is the same thing as the solubility product, you usually just consider the product side, and that makes sense. Now let's look at common soluble salts, common sparingly soluble salts that we will be taking as examples in the course of this video. So we'll take the expression for solubility product of these salts. Number 1, AgCl. Number 2, BaCl2. Number 3, BaSO4. Number 4, CuiO3 2. Let's use this 4. So we want to write the equilibrium constant for the solubility product of these sparingly soluble salts. If you remember very well, you can think of these salts. Of course, all chloride salts are soluble except mesylego, that is mercury chloride, silver chloride, lead chloride, and gold chloride. Okay, then you talk of sulfate salt. All sulfates are soluble except Ba and Lp, that is bale. I mean, those of you that are football fans, you are a bale. So you talk of barium sulfate and lead sulfate. And then you talk of this. So basically, these salts are allegedly sparingly soluble. And now let's learn how to ionize them. To ionize this, don't forget, let me help you out this. AgCl, the subscripts are just 1, 1. So each person has 1, 1. That means Ag plus Cl minus. So we're going to ionize this to get Ag plus and Cl minus. Don't forget, all of these are solids because they are sparingly soluble, and the ions are going to be aqueous. Now you look at BaCl2 as well. What should you expect? Alright, you are correct. BaCl2, we have 1, 2, so we have Ba. This 2 comes here, 2 plus and Cl minus. Okay, how many chlorine can we see here? We can see 2 of it. How many barium? Just 1. So this is going to become Ba2 plus and 2 Cl minus. Aqueous, aqueous. Okay, now for the third one as well. Now this may be a little bit tricky because there's no subscript yet. We still have to do something. Now Ba and SO4, of course, when you split it. Now you definitely know that this is Ba2 plus. So this is Ba2 plus. Now what will happen? I mean, it's even conventional that you always know that SO4 and CO3 are always 2 minus. SO4 2 minus, CO3 2 minus. But this is not showing 2. So why is it that way? The reason is that when elements combine, addition is simple whole number ratios. So if it is 2, 2, because they are same 2, 2, they will break down to their simplest ratio, which is what? 1, 1. That's why it became BaSO4 without, instead of writing Ba2 SO4 2. You get that? So of course, when you analyze this, is going to become Ba2 plus and SO4 2 minus. Aqueous, aqueous. And now finally to the last one with ionization, which I believe makes it very easy. I'm approaching it from this stance so that it's going to be easier. Now we have Cu and IO3. When you split that up, okay, so now this is 1 and 2. So exchange it, you're going to get Cu2 plus and IO3 minus. But of course, from this, you have 1 Cu, IO3 is 2, so this is going to be 2 IO3 minus. So you're going to get Cu2 plus 2 IO3 minus. Aqueous, aqueous. Alright, so we're good. Now we can ionize all of these compounds. If you think that you are lost in because of this ionization, do pause the video and write all these things, attempt them in your book and check back on the video. You can go back and see if you were correct. Alright, that's good. Now the next thing is we can ionize our compounds. How do you write their solubility product, or how do you write their equilibrium constant? Okay, so makes it easy from here. Write the KEQ, which is the same thing as the KSP. Don't forget, we only write aqueous or gases. We don't deal with solids or liquids because the activity is one. So for this now, AgCl now, product over reactant. But don't forget, because all the reactants are solids, I'm going to be concerned with the product. So we are going to have Ag plus and Cl minus. That's for number one. For the second one, question 2, we are going to have Ba2 plus and Cl minus. Now I did not write 2Cl minus. I wrote Cl minus. The 2 is supposed to be what? A product, a power of the concentration to give us activity. So Cl minus raised to power of 2. Now the third one we have likewise Ba2 plus and SO4 2 minus. The fourth one we have Cu2 plus and IO3 minus raised to the power of 2. Alright, so now you see how easy that can be once you know it from the foundation. Now we've not even gotten to the calculation part, which is usually like the common questions that you can come across both in your UTME and in your post-UTME, as well as some of your O-level questions. I mean, talk of NECO, talk of WAEC, and the likes of them. Alright, so this is the solubility product. Now that you can write this solubility product, the work is about 75% done. So what do we need to do next now? Let's take questions on calculations of solubility products. Alright, so we'll be back to this soon. Let's write down the question. The very popular question that is in your past questions. I'll go with the first question on silver chloride, AgCl. Alright, so we have that given that the solubility product of a sparingly soluble salt AgCl, okay, let's take it this way. A saturated solution of AgCl, I mean, what's AgCl? That's silver chloride. I don't want to waste time writing silver chloride. At 25 degrees Celsius was found experimentally to have solubility product of 2.0 times 10 raised to power minus 10 mole squared dm minus 6. What is the solubility of the salt at 25 degrees Celsius? Now in this case, we have the solubility product of the salt, but we are looking for the solubility, which is equivalent to the concentration of the salt, right? Now, solution, of course, the way it's done in secondary school, you write your mathematics, and then if you don't write solution, it looks like you're not doing anything. Now, you look at this question, of course, it's a saturated solution of AgCl, but of course, why are they adding this saturated? Remember, under your water and solubility, saturated solution, it has dissolved particles in the it contains as much as it can dissolve in the presence of undissolved particles, meaning that although it is soluble, it still has a lot of undissolved salts. Do we get? Alright, so we'll come back to this, and saturated solution means that AgCl is going to be sparingly soluble, and then when we ionize it, of course we did that already, that's why I went with that approach. Aqueous. Now, they've given you the KSP to be equal to 2.0 times 10 raised to minus 10 mole squared dm minus 6. So I'm going to come back to why this unit is like this. Now, what's the solubility of the salt? Now, that's not even much of my problem. The first thing now is, let's write the KSP. Okay, the KSP equal to Ag plus and Cl minus. Alright, now we now tend to think that they've given us KSP. What is now the concentration of each of these things? Since it's a saturated solution, of course, which most of the times will always be, and this system is said to be in equilibrium, the rate of forward reaction will be equal to the rate of backward reaction. So the concentration will also follow this. It's not like the concentration is constant, but it's proportional. Think of Gay-Lussac's law: 1:1:1, right? 1:1:1. So this is X, therefore this is also going to be X, and this is also going to be X. Perfect. Now the next thing is, since we know that the concentration of this is X, put it here, this is X, put it here. So what's KSP? 2.0 times 10 raised to the minus 10 equal to X, and this is also X. So we end up that 2.0 times 10 raised to the minus 10 is equal to X times X gives us X squared. Alright, now what do you do next? You take square root of both sides. Square root cancels this, so in the long run X will be equal to 1.414 times 10 raised to the minus 5 mole per dm cubed. Now, how did I come back to mole per dm cubed? When you put this into it, square root of mole squared will give you mole. Square root of dm minus 6 will give you dm minus 3. That's how we think about this. We'll still come back to how did they even come back to determine that this thing should be square and minus 6. Is there any question on that? You can quickly pause the question and go back to practice this again. Are we good to go? Alright, now that you have attempted that, I believe that you got that answer right. Now there's another question that you'd find in Lamlad. I think that's one of the examples where they are explaining Lamlad chemistry, where they are explaining the same solubility product. So let's take that question too. I mentioned earlier that I'll get back to you on how we get mole squared dm minus 6. So that's what we are going to be looking at now in the next question. So question 2, a saturated solution, okay, because of time. A saturated solution of AgCl has a concentration or solubility, either ways, of 1.414 times 10 raised to the minus 5 mole per dm cubed. Although I'm using 1.414 because I don't want to use calculator, it's easier to go with that value. Now, in your lambda, you come across 1.35 times 10 raised to the minus 5. And, but I don't want to be using my calculator here. So 1.414 times 10 raised to the minus 5 mole per dm cubed. Now, what is the solubility product of the saturated solution? Of course, there will be a temperature. Alright, so the same pattern. The first thing to always do is ionize your salt. Okay, so it's going to give us Ag plus Cl minus, and this is X, X, X. So what will be our KSP? That's going to be Ag plus and Cl minus. We good. Now the next thing is you are looking for KSP, so it is equal to what's Ag plus now. This X is the concentration. Whatever is the concentration here is equal to the concentration equal to concentration. That's why we have X, X, X. So the concentration was given to be this one, 1.414 times 10 raised to the minus 5. Now the unit is what? Mole per dm cubed. Keep that in mind. We'll come back to it. And this is going to be X, and this is also going to be what? X. So KSP will be equal to X times X, X squared. What's the value of X given? The value of X is 1.414 times 10 raised to the minus 5. So I'm going to square it. Now, when you are squaring this thing, what's the unit? The unit is mole per dm cubed. That means the unit will also be squared. So when you square mole, mole raised to power 2 becomes mole squared. Dm minus 3 raised to power 2 becomes dm minus 6. Please, this is indices, not integral numbers, not naturally occurring numbers. Because normally you say 3 squared is 9, but that's not the case here. This is an indices or index form. So minus 3 times 2 minus 6. Alright, so KSP here. So that's how we came about the unit that I said I was going to come back to explain. So it means if X was raised to power 3, it's going to be mole raised to power 3 dm raised to power minus 9. So KSP will be equal to square of this is 2, and square of this is 10 raised to power minus 10 mole squared dm raised to power minus 6. As easy and cheap as that is, you've been struggling with it all the while, and now you are good. And that's one more reason why you need to subscribe to the channel, put on the bell for all notifications, and of course share this link with your friends and every other person that you think will need this for subsequent concepts. Now, the next example, now we go down to another very technical example in LAMNAD. LAMNAD is just a bank for your questions that you can always go back to. So I refer to LAMNAD most times. For your O-level exams, you should always look at LAMNAD chemistry and new school or other biochemistry. Okay, so now for the next example, that's going to be like our question 3. A saturated solution of BSO4 has a concentration of 4 times 10 to the minus 5. You have to look for the solubility product. So a saturated solution of BSO4 has a concentration of 4.0 times 10 to the minus 5. What is the solubility product? Alright, we're gradually moving and we're getting to the end of this. So by now you should be you should have attempted this. Attempted before me. Alright, so this is BSO4, you have Ba2 plus and SO4 2 minus. Now, but don't forget, this is X, this is X, this is X. So the KSP is equal to Ba2 plus and SO4 2 minus. So your KSP is what we are looking for. This is X, this is also X. So that is X squared. And what's our X? Concentration. So 4 times 10 raised to the minus 5. When you square this, you are going to get 16 times 10 raised to the minus 10, which is the same thing as saying 1.6 times 10 raised to the minus 9 mole squared dm minus 6. I believe it's very, you got this as well, as cheap as that is. Now the next one as well, I think I have 2 more examples to go. Is it two? No, just one more. Let's take one more and then you can go and check out other examples. If you do not get it, bring it down and comment under this video in the comment section. You definitely get a response to that. Or of course you could simply reach out to us via our official handle to join our community of active learners, where you have people that are constantly brainstorming with you, and or join our classes where people are actively learning. We have expert tutors on ground to put you through that. It's definitely not free, but of course reach out first. That's the first step to success. You definitely take a step. It's not as expensive as you probably think it is. Now we go down to the last question for the day. CUIO32. In UI POST-UTME 2020, this particular question was asked, and of course, many of us, we already assume that of course it's the no calculator system. So I did not even know that there was a calculator in the exam hall. You just have to be smart. So let's see how that's going to work out. So a separated solution of CuIO32 was found experimentally 25 degrees Celsius, was found experimentally to have solubility product of 1.08 times 10 raised to the minus 7 mole cube dm minus 9. Yeah, this is the value. 1.08 times 10 raised to the minus 7 mole cube dm minus 9. The thing is, this question is actually in LAMNAD, but it was not CuIO32. In LAMNAD exercise, it was MX2, but in the POST-UTME it was CuIO32. So if you have actually done it in LAMNAD, then you find it easy to do in any exam. So that's just the trick. And then you go out to the exam hall, you come back, you say that they don't repeat any past question. It's just all about you cramming. It's not about you cramming the past question. It's all about you solving to gain knowledge. Now, 1.08 times 10 raised to the minus 7 mole cube dm raised to the minus 9. You have to find the solubility of the salt. All right. So solution as usual. Now we are dealing with CuIO3 so you have CuIO3 reversible because it's in equilibrium. Have Cu2 plus and IO3 minus. But how many moles of this? 2. I believe you are already thoroughly grounded on how to do this. Now, if this is X, 1 mole is also going to be X, 2 moles is going to be 2X. I take that again. 1 mole of Cu in this is X. 2 moles of IO3, so IO3 is 2X. Now, assuming you do not have this, let's just go from there. What's going to be the KSP? KSP is going to be Cu2 plus and IO3 minus this one too. Abi, that's activity. It is not this charge that is the power. It is the what? Number of moles. Now let's come back to that. X, X, 2X. So you don't go and say that this one is not having 2 plus. No. It is the number of moles that is the power. Now, you now come back in. They give us KSP 1.08 times 10 raised to the power minus 7. And what's Cu2 plus? That's X. What's IO3 2 minus in this? That's 2X. But don't forget that there's a 2 as this part 2. This is where most people get it wrong. They assume that no, if this one that have 2 plus, it's not that should be 2x squared. No, this 2 is not by virtue of the charge, it is by virtue of the number of moles that we have in our equation. So the next thing now is expand this. What do you have? X is here, 2x squared. Don't do the mistake of putting the square inside the bracket. It's for everything. So 2 squared is going to be what? 4. X squared is going to be what? X squared. Now the bracket can now be. So what do you do next? You open this. X times x squared. You get 4x cubed. 1.08 times 10 raised to the power minus 7. Now this is where your calculator or your mathematics genius comes in. In mathematics, you know of standard form and you know of indices as well. Okay, now we want to see how we want to make this number a whole number. If you have 108, you know the next thing is to divide both sides by 4. So, but imagine dividing 1.08 by 4, it may be quite hard. Although it's still easy. I mean, 1 over 4 is 0.25, then 0.08 over 4 is going to be 0.02. So you end up with 0.27. You are still on a very perfect headway. But what if you don't want to go that way? You can just go ahead and say that you want to convert this thing to 108. And if you make it 108, is it going to be 108 times 10 raised to the power minus 9 or 108 times 10 raised to the power minus 5? Why? Because we are shifting 2 things behind. So is it going to be 108 times 10 raised to the power minus 9 because 2 things have come, or 108 times 10 raised to the power minus 5? I mean, so let's confirm. If you have 108 times 10 raised to the power minus 9, in standard form that's going to become 1.08 times 10 raised to the power 2. 108 is this. Then what you have left? 10 raised to the minus 9. How do I get this 10 raised to the power 2? 108. These 2 things, when it goes back, is what we have. It's just like saying 1.08 times 100. Now this other one is 1.08 times 10 raised to the power 2 times 10 raised to the power minus 5. Now, in standard form, of course, or indices, 10 raised to the power 2 times 10 raised to the power minus 9 is going to become 10 raised to the power 2 plus minus 9. When you have 10 raised to the power a times 10 raised to the power b is 10 raised to the power a plus b. If it is division, it becomes negative subtraction. So now 2 plus minus 9 is going to be 10 raised to the power 2 minus 9, and that's 10 raised to the power minus 7. So we are going to end up with 1.08 times 10 raised to the power minus 7, just like we have in our question. But if we go with this, we are going to end up with 1.08 times 10 raised to the power minus 3, which is actually not correct. So the first way to do it without your calculator is pick this 1.08, divide it by 4, 1.08 over 4. Remove 1. If you divide this number, you're going to have it as 1.00 plus 0.08. That's how we came about this. So we divide 1 by 4. 1 over 4 is 0.25 now. 0.25. 0.08 over 4. 4, 1, this is 2. So you are going to have 0.02. When you add everything together, you get 0.27. Do you get? So if you have 0.27 here, okay, let me assume that I'm using this over 4. I will have let me come back to the top. Don't forget, all we are using now is 108 times 10 raised to minus 9. So we are still going to use that as well. So this is going to give you 0.27 times 10 raised to power minus 7. Okay, equal to x cubed. This has cancelled this. So now, to make it easy, convert this thing back to standard form. If it becomes 2.7, now 0.27 in standard form is 2.7 times 10 raised to minus 1, abi, or 27 times 10 raised to minus 2. So this thing, let's make it 27 times 10 raised to minus 2 times 10 raised to minus 7 equal to x cubed. Minus 2 minus 7. When you have multiplication, it becomes addition. So this becomes 27 times 10 raised to minus 2 plus minus 7. Minus times plus will become minus. So minus 2 minus 7, that should give us what? Minus 9. So 10 raised to minus 9 equal to x cubed. What do? Take cube root of both sides. Cube root of 27 is simply, what will you multiply 3 times to get 27? That's 3 times 3, 9, times 3, 27. So that is 3. Cube root of 10 raised to minus 9 is, what will you multiply 3 times to get 10 raised to minus 9? 10 raised to minus 3 times 10 raised to minus 3 times 10 raised to minus 3. That will be 3 plus 3 plus 3. That's 9. So this is going to be 3 times 10 raised to minus 3 mole per dm cube. That is the concentration of the salts. That's if you are using this method. Alright. Now the other way that I was trying to explain is if you want to use 108. Okay, so you have 108 times 10 raised to minus 9 equal to 4x cubed. We've converted this. Go back to the video and see how I converted that. So what do you do there to divide by 4? Divide by 4. So 108 over 4. Okay, 4 and 10 is 2. That's 8. Remaining 2. Put the 2 in the back of 8. That's 28. 4 and 28, 7. So you end up with 27 times 10 raised to minus 9 equal to x cubed. And then you still take the same cube root, you arrive at the same answer. Alright, so that's everything that you have. I would advise that you go back to your landmark chemistry and go and solve that example on MX2. So, and you can also write out all of these examples that we've solved in this video and you know, try to solve them yourself without checking the notebooks to solidify your understanding of the topic. And of course, don't forget, if you've not done so, please click on the subscribe button, that bell, the bell button, click on it and show notification for all videos. After that, the next thing is to share the link to this video with your friends, on your WhatsApp status, on your Facebook, on your groups where you have a group of learners, and of course tell them to also follow this channel.